recording these for YouTube and stuff like that just makes more sense to keep them like a clean audio recording. And we'll get started. So this is what we'll be ending up with today. And I'll just go through it kind of step by step. So at the start I was saying there's a few different things going on. So there's a few different shapes being drawn, the box, cone or pyramid, face. Dubtronics, thank you for the 5 months, tier 1. Let's go. So we have the face, the box, the cone, and the sphere. And then there's the transitions or morphing between the two. You can see that it's kind of hard to tell in some of them, but there's a jiggling motion, and then the morphing is offset over the height or the elevation of the shape. Shrubber Knee, thank you for the tier 1. Thanks everyone for subscribing, supporting this content and stuff like that. I am actually working on some additional subscriber benefits, hoping to make an announcement with that, I don't know, in the next week or two or something like that. Just some additional bonus material. Yeah, thanks to everyone who's been watching on YouTube and then made the jump over to the live audience. Bread and butter. So yeah, I mean, it's cool to be able to transition and stuff like that between different shapes and morphing, and then the kind of like sparkling or fairy dust twinkling effect with the points. So we'll just jump into that now. So I've been setting up these wrangles in different methods for what we've been creating. For this one, just generating all the points at the start. This point generate will just create 5,000, however many points you set. It will just generate them all. It will put them just all at 0, 0, 0, or the origin. And then you can run the wrangle in points. So what this does is just multi-thread, or however many threads your processor has, it will run those points in parallel. So it can it's just more optimized to do that. If you do run over detail or only once, then it's a bit slower because it's like single threaded essentially. So if you can, like certain scenarios, like last week's with the nested things, they were all based off of the previous parent. So you couldn't multi-thread that as well. So that's why I was running it in detail mode. But for this situation, basically all of these points don't need to know anything about the other ones. So you can just run your program in parallel. So that's why we're just running this over points and generating all of these at once. So we'll just build off of kind of what we were doing last week. We're doing the circular coordinate scheme. So if we took the p.x and set that to a sine, do sine of, what I'm going to do here is just generate a random number per point. So we start to see something there. What's happening here is it's not even a full oscillation. So the sine we know goes from +1 to -1 and then back to 0. So each point is getting a random number generated. The result is between 0 and 1. If we want to get a half circle or a half oscillation of the sine wave, we can scale that to pi. So what that did was expand this to go forward and backward. So it's doing like 1/2 swing of a pendulum. And then if we want a full sine, full repetition, you can multiply that by 2. So in one dimension now we have this kind of drawing like a circle. We're just going back and forth like a clock, an old school pendulum. And then if we want the circle, we can just keep going with this and switch this to Z. So right now this is like a pendulum that's synced up in both directions. If we switch from sine to cosine, then we'll get the proper circle. So again, that's just half. Cosine is the same as offsetting it by pi or half a revolution, essentially. So this is how you can get a circle or a perimeter. So just say sine, cosine, circle. And if we keep going, just a refresher, one of the things we were doing last week was the spiral. So if we want to, we can say our radius, or r, is equal to another random number. I'm going to offset this one just by some kind of arbitrary numbers. So that just makes sure we get a different result than these two random numbers. And then if I end up scaling these or multiplying them by r, or the radius, then you see right now we just have this like disk. This is kind of like this spiral. I think if we actually did this without offsetting with a random number, then we'll get the spiral. So then if we just want like a disk, then we can offset with the different seed. So when you have all of this, these are all the same random number, essentially. They're sharing the same result. So over the circumference, or the perimeter of the circle, it's getting expanded outwards. And then this one, because we've offset the random number, basically each of these is getting pushed in or outwards by a random amount, if that makes sense. So this is just a few different ways to draw the shape, essentially. So keep going here, and then this one, we're actually going to go into spherical coordinates. And some of this stuff you can look up because it's not just the way that Houdini's not used like universally, I guess. If you look up the spherical coordinate system, they'll talk about it here on Wikipedia. And basically Cartesian coordinates, this is like X, Y, Z, just traditional kind of coordinates that you're used to with every 3D application. And then if we want to go into the, where did it go? Should be somewhere in here. Here it is. So this is for the spherical coordinates. You can see this is written, it's a little bit kind of obfuscated or not VEX code. It's just traditional kind of long form like math symbology, or whatever you want to call it. But basically this is where I got this from. So this, I believe this 0 kind of looking thing is called the theta. And then the other one is called phi. This is basically like UV coordinates. It's just two extra variables or two extra numbers. And then R is what I was using originally, like the radius. So what I could do up here, we have R. And then I'm just going to keep going with, we'll keep with the lingo. We'll call this theta, generate another random number, and phi. And then this one, generate another just random number. So again, the arbitrary digits here is just to make these unique random numbers. Otherwise, they'll all be the same random generation if you don't offset them. And then you can look here that they're setting x like sine and cosine. So that's like the circle kind of stuff that we've been used to. But then for y, they're doing both of them as sine. And then for z is just the cosine of theta. So if we want to just go ahead and do that, what we can do, I'm actually going to set r to 1. So it will be on the edge of the circle instead of like random radii. So we have p dot x, and we want that to be sine of theta times the cosine of phi times r. And you just keep this organized. The other thing we want to do is make sure we're scaling these to be 2 pi. So I'm just going to keep doing that at the top. And should be good with x there. Then if we just keep looking here at this page, for y, they have it set to sine and sine of theta and phi. And then you can see we're getting like a 3D disk, or I guess a two-dimensional disk or two-dimensional circle. And then for z, just doing the cosine of theta. And then we have our 3D circle or spherical coordinate system. So this is kind of what's known as like another space, essentially. We have like Cartesian space, and then this is spherical space, or sometimes people also call it polar space. I'm just going to keep this multiplied by r. And then if we want to switch, Houdini works with the y-axis being up and down. So if we want to keep carrying on with that, what I can do is just switch this to z and move this one to y. And then our poles with the top and bottom of the circle is kind of oriented to this. It just makes more sense. So it's like if you use the sphere node in Houdini, orientation, you just go over to polygon, mesh. So it's like the orientation here, why we were oriented with the z-axis, along the z-axis essentially before. So we'll just say this is spherical coordinates. So one of the reasons people use this kind of stuff is like, looks pretty similar to planets or things like that. Theta and phi are pretty similar to actually latitude and longitude. So if we could just take theta and override it to just pi, you could see then we're all basically at the South Pole. If we maybe divide this by 2, then we're right at the equator. And you keep going, maybe divide it by 4. You're halfway between like the North Pole and the equator. So this way, it's a little bit easier to refer to like a location on a sphere in 3D space without having to, if you were trying to just use this by manually setting x, y, and z, it would be pretty difficult. So this is one of the reasons that people will use other coordinate systems, essentially. If you're used to using 3D applications or whatever, you probably used UV coordinates. And this is a similar idea. I'm just going to put down the test geometry, or the head. And if you go over the viewport in Houdini, you press the 5 button, then you'll see this is in UV view or UV space. Vegan nuts, how's it going? So this is very similar to kind of mapping or stuff like that, I guess. If we look at maybe it's like the Mercator projection. I guess just different projections. If you're unwrapping a globe or a sphere, you're just mapping the coordinates onto like a 2D plane. So now if you just have an X and a Y coordinate, then you're referring to, you could also translate that to like a latitude and a longitude. But basically what I'm saying is like these are all referring to the same final kind of position, but it's just using different coordinate schemes or different ways to refer to the positions. So obviously these are like relative to where you are in 3D space, it kind of makes sense to use one or the other. So like for us, we're somewhere on the surface of this planet, and it makes sense for you to say I'm on like the 38th parallel. GPS coordinates or stuff like that is latitude and longitude. And then if you want the radius, for us, that's like the elevation, or how far away you are from sea level, or the distance of the origin of the sphere. If we were all like astronauts and we were on a different planet, then you might want to use like 3D coordinates. Obviously that gets a little bit more difficult though, because like the planets are spinning. They're on an axis that's tilted, so like you'd always have to keep updating your 3D coordinates over time, and like it just becomes very complicated. So that's one of the reasons, or there's several reasons why you might want to use different ones. Texture mapping is a similar idea. If we assign a texture or a image to this guy, and it's a character that's deforming and moving, you want the texture to stick. So this is the same idea as like the Earth is spinning, but you're referring to a constant position on the surface. So using UV coordinates, you can stick a texture or refer to, you basically have this map, or the UV map, or the texture space that refers to a fixed location on the surface that's separate from its 3D coordinate system, if that makes sense. So this is just one of the reasons why you might want to use these other coordinate systems, or why they were invented, and why they were used in general. Just say latitude. If we wanted to do the other thing, that's helping. Yes, it's all just unwrapping 3D space, or kind of defining your own coordinate schemes, I guess. So we'll do phi now. We can set that equal to, you don't have to do it based off of pi. You would do it from a fixed number. So you can see we're referring to specific longitude. So this one I was calling latitude. It's like the equator or stuff like that. It's just horizontal versus vertical, essentially. And then if you do both of them, then you can manually like pick a specific point in 3D space. So it's like if you do Google Maps, you do, I don't know where you want to look specifically, but clicking, you can see at the top, this is giving us pretty specific coordinates that are separated by commas. So this is the same idea as these are specific latitude and longitude coordinates that you can refer to a specific kind of marker or like a point in 3D space. If I drop this guy down, then we're kind of now in 3D space or whatever on the surface of that area. But this is still giving us specific kind of X and Y or UV, theta, and phi, just latitude and longitude coordinates. Maybe if you do Google Earth instead of, I don't know if I need to install it, but this might make a little bit more sense because then you can zoom out and like actually see the 3D sphere. Vegan Nuts, we made it to 1K followers. We popped through the limit. So yeah, this is 3D space. And then I don't know, maybe I'm doing a bad job working this or whatever. But basically these are referring to specific latitude and longitude, kind of like that is before we specified these locations or these coordinates is like that. So just like if you use a GPS or you've ever seen those coordinate systems, this is kind of like why they get used or one of the situations where they're used. One thing you might notice though is like there's some seams or uneven distribution at the poles. And that's just an artifact that you get the way that we're randomly generating numbers for theta and phi this way. If you want to do another thing using this wrangle, they actually have a special vex function. It's called sample direction uniform. And then this takes two arguments, kind of like theta and phi, but for this situation, it can just be like two random numbers. So if I just say set, this is going to be one random number. And then this is more like UV coordinates, I guess, like U and V, numbers that are between 0 and 1. We'll just do another random. And then I'm just offsetting these so that they're different numbers. So now you can see this way we're able to sample a 3D direction, and the result of this is locations that are on a sphere. I think even with this, if you want to manually set them, you get kind of like the hemisphere or half the sphere and stuff like that. It's a different way to refer to things. So this is how you can avoid those seams or the uneven kind of pinching at the poles or stuff like that. This gets used for a different reason. So this is like mapping for locations. It's very easy to know latitude and longitude where you are in 3D space. This one is more for random 3D directions. So if you're going to be spraying stuff randomly in 3D, you obviously don't want to be shooting more stuff towards the poles. You want to be completely randomly sampling things. Also for rendering, if you're doing reflections or ray tracing or stuff like that, you want to use one of these functions that's not going to be biased or pinching stuff in 3D space. So there's a whole library of these sample functions that can be pretty useful. So like another one, I think it's sample circle uniform. So again, this is like 2D space. With the disk up here, you could see I had the same issue with some pinching at the poles or with the center. So if you, depending on what you need, you could sample randomly a disk this way if you don't want to get any pinching or kind of like stacking up or stuff like that. So this is sample circle uniform. So if you're looking at this starting thing, you can kind of get an idea where some of these shapes came from, how we might be sampling them or getting to them. So with the box, they don't have a built-in function that can do it, but if you kind of know your tools or stuff like that, you can kind of hack together your own. So we'll just say sample box surface. And always in the past, we were using this random function to generate a random number between 0 and 1. Yeah, sorry about that, I forgot. Yeah, if you fell behind with any of the code or stuff like that, just put this in the folder. This is just going to be week 4, start. Let's see if I can get to my shelf. All right. So yeah, if you grab that, you can get caught up with some of the earlier functions. So we'll just keep going with the box. And we were always doing these random numbers to generate like already had it. All right. So if we do p.x with a random number, we get random numbers there between 0 and 1. If you want to, you can just set p or a vector to a random number, and this automatically will generate random numbers. Each component will get a unique random number. So it's basically generating a 3D random number. And the result that you get is like a 3D box. So if you really just want 3D space, 3D box filled with points, it's pretty easy with just this simple function. If you want to sample the surface of the box, it gets a little bit more complicated. So what you can do is, I think you can just take like, see what happens with this. So if we do, there's a few things I did there. I switched this to p.x, so just one component. And then instead of a random number, I did this rint. And that basically rounds to the nearest integer. So rint stands basically for round to integer. So anything that's less than half gets set to 0. Anything that's more than half gets set to 1, or placed over there. If we keep doing some of this, I think we could set p.y to then you can see we're either getting 0 or 1, or we're getting kind of the corners of a box eventually. What I'm going to do is actually get rid of that rint stuff for now. You can see if we just do two coordinates, then we have a two-dimensional surface or rectangle or whatever filled with random numbers. And if I did p.z, now we're back to the full 3D box. This right here is the exact same thing as just doing it once. So if we do P, you get the similar, the seeds or the random numbers generated are slightly different, but the end result is essentially the same. But if we take one of these and round them to an integer, then we get the edges. So we do it to p.z, and we have the sides of the z axis. If I did this up here, and do it to this one, the y, then we flipped it, and we're just getting the edges there. And then again for x, if I just keep doing the same operation, so we have the sides there. So we're close to getting the surface of a box. We just want to randomly get each axis, or 1/3 of the points do this, 1/3 of the points go for the y-axis, and 1/3 go for the z-axis. So this is a little bit of a weird hack, but we'll go ahead and do it. What I'm going to do is generate an integer. We'll just call this like axis, and make this another random number. You could offset this if you want. I'm just going to leave it how it is right there. So this is green right now, or it's kind of yelling at me because it's basically saying this random number generated is giving you numbers that are between 0 and 1 or decimals, but you're storing them in an integer, or you're storing them in a data type that doesn't have or support decimals. So I'm just going to get around that and do, could do rint, or you can also do floor, and floor will just keep the lowest nearest number. If you ever want to do some like debugging or investigate these variables, sometimes I'll use this kind of trick or method or whatever. So basically, this @ symbol is making an attribute, just so in this spreadsheet I can visualize the result of things. So we're doing the floor, and that's just making all of these decimals get pushed down to 0. If you want to get random between 0 and 1, you can just multiply this by 2. So now half of them are 0 and half of them are 1. Hopefully this is making sense. Hopefully I haven't made it too unclear. Then if I go up to 3, then basically what we're getting is like 33% or 1/3 of them are zeros, 1/3 of them are 2, 1/3 of them are 1. So if you think of this axis now as like 0 is x, 1 is y, and 2 is z, then we have our random sides of the box that we want to pick. So if I set the, we could set p.x equal to rint more dense illuminated. There wasn't too much that I was doing to the edges to get them special. I think it's just with 3D space, the way it was working. There are functions you can do to boost edges if you want, but I'm not going to be covering them here, unfortunately. But yeah, I think this was just an artifact or basically unintended kind of result of how I scattered them. So yeah, this is how we get one of the edges here using p.x. One thing you can use instead of .x is if you use these square brackets, then you can refer to the component as like 0, 1, and 2 for x, y, and z, like that. So we can do the same thing over here, like that. And then with this axis, what we can actually do is just replace this and randomly sample or randomly get the edges this way. So if you've done kind of investigating or debugging this result, you can delete that or just eliminate it or whatever. And if you really wanted to be cleaner or more optimized with your code writing or whatever, you could go up here and eliminate this to just generating a 3D random number that way. So it's just less lines of code for people to parse through or to look through. So this right here is just generating a random number between 0, 1, and 2. And the distribution of them should be like 1/3 is 0, 1/3 is 1, 1/3 is 2, and so on. So hopefully people are still following, or hopefully it hasn't gotten too confusing so far. Let's move on to the cone. So essentially this only gets the surface points for a box. Yeah, this will only work for kind of rectangular systems. If you want to kind of combine some of the stuff we were doing in the earlier weeks, one thing I did was like non-uniform scaling. So if we want to do uniform scaling, you can obviously just multiply by a number. We get something that's twice as big. If you want to do 3 numbers, or we could do a channel vector scale. Now just click that drop down, and anytime you have a channel reference like this, it will look at the name and make a parameter set that's automatically named that way. So this way, you can make your 3D boxes or 3D rectangles or whatever you want. So yeah, this is kind of a hack for getting like an even distribution on a 3D box or a 3D rectangle. So you can use these functions over here for spherical systems and stuff like that. There just wasn't a function built in, so I was just kind of hacking this together myself. Yeah, so we can go down to the cone next. And just gonna start with this circle here. Yeah, so if you're familiar with kind of 3D, getting a good way, I guess, to get familiar with 3D geometry, or how it's constructed, is like a lot of it can be done by putting together some of these basic functions. So like here we have a circle. If we set the height equal to a random number, just keep offsetting it, then you start to have a cylinder or a tube or something like that. So just thinking about scaling and math and stuff like that, hopefully eventually you could start to put mix and match some of these functions and stuff like that to get the result you're after. And then if you look at some of the stuff, like our elevation now, or our y, we have height between 0 and 1. One thing we could do is generate, I guess I'll just keep it this way. So if I multiply the x axis by the height, we've kind of flattened this down in one dimension like that. Then I'm just going to keep doing that with the z. I think I've messed this up a little bit. So I wanted to do multiply equals. So what we're doing now is pinching it, and everything that had 0 height is also having 0 radius as well now. So you could just comment this out. We're pinching it in one direction and then not doing anything at all. So we know our height is going from 0 to 1. We could also do this 1 minus to flip this around. And then we're just getting the top of it. And then if we want to do the same thing over here, then you're getting kind of a cone or something like that. So just mixing and matching some of this stuff, you're kind of doing, mimicking 3D operations. So like this right here, if I multiply this by a channel, what I can do is call this extrusion. And this is kind of like the height of a tube or a cylinder, or extruding a 2D shape along an axis. In this case, it's the height to get a 3D extrusion. So if we're working with this circle, we can start to do the similar stuff. One thing I want to do here, this is another kind of thing like we ran into with this 3D circle. Originally when I made it, it was aligned along the z-axis. This disk, the same thing is happening, is that if I just click, the z-axis is just left and right. So it's facing or sitting kind of on the z-axis. If you want to rearrange the coordinates, what you can do is say at p equals at p dot x, z, y. And this is kind of flipping them around. This is a shortcut, or it's a bit of a fancy syntax for doing something that's a bit more long form. If you've worked with VOPs or stuff like that, what that's doing is basically taking a vector to float and a float to vector. And then what I did was zx at p equals dot x zy, I believe. Let me just double check. X, zy. So x, z, and y. So it's just doing like a shuffle or switch or whatever. There's actually a special name for this that's called the swizzle operation. So if you want to do it with this, this is basically what I was doing. The swizzle is traditionally a programming like code concept. So the node, I don't use it as much. If I do it, sometimes I'll do it using these because it's a little bit more visual, seeing the connections. But it's the same idea here, typing it out. If you search here for just swizzle vector, this is a common operation that isn't just specific to Houdini. other programming languages and other people will use it as well. So it's just the same visualization and stuff like that, I guess. Maybe it's a fancy drink as well. But yeah, if you're just visualizing it mentally, like I'm just thinking about it like this, as you're rearranging the inputs and the outputs essentially. Does that hopefully make sense? So you're saying the x is equal to x, the y is equal to z, and the z is equal to y, or the first component is x, second, all right, going on too long about it. So now we've just rotated it, shuffled it, plugged in the different outputs. Just swapping, if you look at this of the spreadsheet, swapping one column for the other. So then if we want to do a height or move things up in 3D, what I can do is take the y position and plus equals. There's a new function we can use. I don't think we've used it before. That's called the length. And what that does is just looks at the distance or how far the point is from the origin. So if I set that, then these points on the edges that are further from 0 are getting pushed up the full amount or 1. And anything that's equal to or close to the origin gets a value of 0, or basically doesn't get moved up at all. This length, you could also think about it, it gets used for different purposes, like for speed, it's like the magnitude, basically the strength of a vector if you're talking about like a direction. With 3D positions, is basically, you could think of it as like the distance from the origin, or from 0, 0, 0. Yeah, hopefully it's still making sense. So then I could keep going and do 1 minus, and we've flipped it around. So basically anything that was 0 becomes 1, anything that was 1 becomes 0. We're just flipping things around like that. And the last thing we want to do is make a bottom to this cone, or a bottom to this shape. So what we could do here is just get half of the points, or 50% of the points, and force the y position or the height to be 0. There's a bunch of different ways to get half of them or 50% of them. It just depends on what you think of first, or what you're most comfortable with. So I could do this, just make a new integer. I'll just start with a float and call this A, just a capital A. Set that equal to a random number. So the reason I'll use capital A for a quick way to debug stuff, after P, your position, the rest of your attributes in this geometry view will get sorted in alphabetical order. So if you do capital A, you should generally see it pretty quickly. If you have a geometry with a lot of other attributes or columns, you might have to like scroll over. So just capital A is like a quick temporary debugging attribute for me. So we have these random numbers we've generated just randomly between 0 and 1. We could do what we did earlier, and what I was doing was taking the floor and scaling this to a random number between 0 and 2. So then you get some zeros and some ones. If we get rid of the floor, you can see now we just have a random number or random range that gets generated between 0 and 2. So then we just do a floor. We have 50% of them as 0 and 50% of them as 1. So if you wanted to, you could just multiply the y position by this. And then half of them multiplied by 1 are basically unchanged, and half of them multiplied by 0 or set to 0 for the y height. Use underscore for my test. Show some reason. Yeah, that's a good idea as well. Sometimes I'll do that for temporary attributes as well. So if I'm doing a series of operations, you could do like, I think double underscore sometimes is a somewhat standard Houdini convention. Like if you do double underscore speed, set that to a number. If you're making a tool set, sometimes this is like reserved attribute or something like that. All comma. Hopefully you didn't miss too much. We're still kind of cruising along. I can do another. Let me just clean this back up a little bit. This will be set the height of half of the points to 0. So this is our cone. So yeah, I'll do a file share. People want to get up to date or they missed any steps or stuff like that. So we have a nice little library here of 3D shapes or different spaces kind of that you could think about as like ways to sample or distribute points onto these 3D spaces. So a nice little tool set. And then the last thing we can do that's pretty cool is looking at 3D geometry. So there's some special vex functions that you can use. One of them is called prim_uv. And what this basically does is every, we just make a grid and we'll just make it four squares, 4 rectangles like that. Maybe I'll just divide it as well and make it like triangular. So each of these triangles or each of these grids is a primitive. It's like a polygon or primitive is the same idea right now. And using the primitive UV is basically, it's a little different than the UV I was talking about up here, like a UV map. This is more of a intrinsic. Intrinsic just means that it is like inherent to the geometry, like it will always belong, essentially. So I think that there was a side effects. I think that there still is. I think another way to think about this is a parametric coordinate. Here it is. Implicit. So implicit is the same idea as intrinsic, to me at least. Is basically like if you have something tangible, something in 3D space, it's going to have a surface area. It's going to have a volume. like even a sheet of paper in real life, it still has some thickness. So there will always be an inherent volume or inherent surface area to anything that exists in real life. So with computer graphics, is the similar idea as like any polygon will have to have these parametric UV coordinates. So each of these triangles like this will have a coordinate scheme to them. That's like 0, 0, 0 for this corner, 1, 0, 0 for this corner, 0, 1, 0 for this corner, and then 0.5, 0.5 for this corner, and so on, or whatever for a quad or for a triangle. So with that visualization in mind, I'm just going to pin it right here for a little bit while I set this up. This prim UV function is a way to retrieve or sample the geometry at this coordinate. So if I say 1, this is the first argument that's going to be the input of the geometry that you want to sample. The next thing is the information you want to retrieve. So in this case, I'm just typing in P for position. You could get other information like the color or any other attribute that you have on the geometry. Then the next argument is the primitive number. So if we have, turn on the numbers here, we have like 0, 1. We just make my font a little bit bigger. All right, so we have 5, 2, 7, 0. This argument here is which primitive you want to sample. And then the last one, I'm going to use set, and that's the UV, or the implicit UV coordinate that you want to sample. So if I do 0.5, 0.5, and 0, then all of these 5,000 points are going to get placed right at that edge, the midpoint of that edge of the triangle. If I do a random number, I just offset it, then you can see it's getting interpolated so that it's like 50% of them or randomly along that axis. It's possible triangles wasn't the best idea. Maybe squares or rectangles is going to be a little bit easier to visualize. You have like 1, 0, 0 for this corner, 1, 1, 0, 1, and 0, 0, 0. So what I'm doing is just sampling. One direction is a random distribution between 0 and 1. The other one is getting set to 0.5 or half. So if I just hand select this, we're just moving it back and forth. This is kind of like the same idea as like longitude and latitude or the equator or stuff like that. And then if we want the full surface, we can just do another random point number. So then we're getting this square randomly. But right now, so far, we've just been looking at the 0th primitive. You could set these to the other primitives you want to sample if you'd like. If you want the full 3D surface, then you can generate another random number. So I've already offset these. I'm just going to leave this one kind of where it is. And right now, we're generating random numbers between 0 and 1. If we keep going, you would see with the green line, again, it's upset with me because I've set an integer or a number that doesn't like decimals, and I'm giving it fractional values or decimal values. So if I do the floor function. That's a good way of just cleaning up the decimals or the remainder. And then if I set this or scale it to 2, then we're generating random numbers that are either going to be 1 or 2. Or you keep going with 3 and so on. If I middle mouse button here, you can see that this has 4 primitives or 4 polygons. So instead of automatically or manually going in and checking that each time, there's another handy vex function that you can use. That's the n primitives. And just punch it in like that. What this does is it will just, whatever input you type in, 0, 1, 2, 3, for each of the inputs of the node, it will tell you how many primitives that input has. So if I set that to 1 for this auxiliary input, then this will automatically tell you however many primitives this node has. So now if I just plug this in up here, this is an easy way to sample, or basically randomly sample, the surface of any geometry. So it's basically, we've kind of recreated the scatter. It actually works. So yeah, if you want, you could do this to random numbers, and you're just getting now either primitive 0 or 1 randomly. So yeah, this is just another way to retrieve information from other spaces. So there's a good thing to know about is this parametric implicit UV space. You can also use, there's a prim, might have to look this up. Let me just go into the functions. I'm sorry, not the language reference. You just go to vex functions. There's a prim UV sample. So what you can do with this is actually look at like 3D UV space, or the UV coordinates that you've defined or mapped yourself. The reason I'm not using them, let me just fix this up. Okay, I'll just turn that off. The reason I'm not using them here is because we have gaps, or there's empty space. So if I was to generate random numbers between 0 and 1, and then sample this geometry by them, we would be finding some gaps or some empty space in the geometry. So that's the reason I'm using this. Just go back to the kind of world space. Just going to go back here to this previous page. We'll just do this as sample implicit UVs. So that's the reason I'm not using the UV coordinates. It's just this is an easy way to sample any geometry, and you do random primitives or a set of primitives and then the numbers, and it will be there won't be any like empty space essentially. So we have different ways to sample other spaces or other geometry here, and hopefully then you can see where we're headed or how we've the track that we're on. So now we could do one more scene distribution, one more share, and we'll keep going on to like the final effect. So we'll just do one thing over here, and we'll just make something a little bit more interesting now. We'll do like this shimmering kind of pulsing effect, and you use it for like dust or stuff like that. It's pretty useful. And I'm just gonna use the color, and I'm gonna set it equal to a sine of the time. So as I play the scene, everything's kind of pulsing or going between -1 and 1. So instead of what we did before was set the output of the sine wave to oscillate kind of 3D space or one-dimensional axis. This is a similar idea, but we're oscillating the brightness of the color. If you want to speed it up and stuff like that, you could multiply time to make it faster or slower. You'd see one of the things we're getting is some negative numbers. If you want to get rid of that, a quick way or whatever is if you multiply it by 0.5, then you're getting random numbers between -0.5 and 0.5. And then if you just add 0.5. So we're taking -1 and 1, scaling it to -0.5 and +0.5, and then shifting it up by 0.5 to get it between 0 and 1. You could also do it if you divide by 2 and add 0.5. It's the same idea. There's a bunch of different ways to get there. I just do this because it's easier to remember is multiply, scale, and then offset, and you just keep doing it by 0.5 or half. And then if we want these to be like twinkling or shimmering, what you can do is offset the time by a random number based off of the PT num, and just another random offset. So you can see it's working a little bit. We still have the issue is this random number gives you results, or generates random results between 0 and 1. This sine oscillates between 0 and 2 pi for one full rotation. So if you want, you would see like certain areas it's easier to see the brightness is slightly offset. But to get the full amount, you're going to want to multiply this by pi and then by 2, or the other way around is the same thing. So now you have these all oscillating at completely independent or random rates. We could do time, just multiply that by 8. Then you have a little bit more quick kind of flickering. Another thing you might want to do, sometimes it's helpful. You could leave some of the numbers going negative, so it gives them a chance to just turn off for a little bit and then turn back on. It's kind of like a break, like instead of always going between on and off of like they're always slightly visible. This way, half of the time they'll be completely off or below 0. Another thing you can do is like a comparison. So if I say, is this greater than 0.9? Then this will barely ever like illuminate them. Now if I could do 0.99, maybe turn the scene, just turn that clock on to have it be real time. So the higher you make this number, the quicker that they'll just blink on and off. Is this kind of making sense? This is saying only illuminate or only display the ones that have a sign output that's above 0.999. So very rarely will we illuminate the points. So we have all those points, but just barely any of them are going to be illuminated. So if we do have them above 0, basically 50% of the time they'll be on, and then the other half they'll be off. We do 0.5, you're just letting them be on for a shorter period of time, and so on. You'd see if I go completely above 1, they're just never meeting that threshold or that limit. And then if you want to, you could just set the number of overall points you have as well to control things. So if you have a particle system or any points or anything like that, and you want to do some kind of like twinkling effect or something like that, this is kind of like sine shimmer, fairy dust, or even particles in 3D space. This is kind of like dust particles or something like that. Basically, with the sine function, you're simulating like a disk that's spinning, and some portion of the time it's like catching the light and reflecting the light and illuminating or becoming bright due to that. So all of these is useful for like dust or particulates or even magical twinkling kind of dust or stars or stuff like that in the sky. And if you want, instead of the color, you can do p-scale. And then I'm just, right now we have our p-scales of either like 1 or 0. 1 unit for p-scale is pretty big. For color, it makes sense because that's like white or fully bright. But I'm just going to do another multiplication here. So this is basically setting the limit to 0.05. And then if I use the D button, we could go to geometry, move this over to disks. And then you can see we're basically doing a similar operation, but we're just scaling them. So if you want, instead of this, you can do it like that. You kind of have these more evolving ones. And you can do different, you could do another way to manage this that's useful is the fit function. So I think I've used this before. This is just handy to remap numbers. So the source range is -1 to 1, and then this output will say to 0 to 1. And you can mess around with this range, kind of like we were doing with the greater than or less than symbol. So this will basically clamp numbers that are less than 0.75 to 0. But instead of comparing and just anytime that it's above 0.75, setting it to 1, this will still transition it or scale it up. So this would be for, what would this be, like 7/8 of the time completely off, and then 1/8 of the time it will be expanding and turning back off. So just a bunch of different ways to handle that kind of stuff or remap it. That's pretty cool. So there's one more component of the big brain. It's just slowly adding more wrinkles to your brain. So this is one more component of how we get to the end here. And then the last one is just some morphing effects and stuff like that. So let's do another scene share. if you guys want to get up to date. And let's just make a simple morph. So I'm just going to do an empty wrangle, morph shapes. So we have this nice like library of codes or shapes or whatever. We have a box right here. I'm just going to go back to points, the D key for display. So we have our box. Just going to grab this code like that. And let's see what else we have is this circle here. So if you look at this box and comment and uncomment out, you can see one issue. We'll just keep going, I guess, right now. We'll fix that later. So we have two different positions. Instead of assigning them both to P, I can store them in variables. So we'll say the vector sphere pose, sphere position equals that. We'll store this in a vector variable before directly like overwriting or overwriting the 3D point position. And we could do the same thing up here, and then this will be vector box position. And if you want to check, you can set this like that, and it does hold the information that we want. So the quickest or easiest way, the simplest way to transition or morph between these is using a function called the lerp function, or it stands for linear interpolation. Just put it like that. So if we take the box position and the sphere position, the last argument is the amount you want to blend between the two 3D positions. Mix in GLSL? Yeah, I think it's mix for Shader Toy, HLSL, or all the fancy business. A lot of these functions are the same, but there's a couple gotchas that I've translated like between GLSL and Vex before, and there's a few gotchas that you need to kind of manually, like the other one is this being Vec3 like that. So yeah, this is just mixing or linearly interpolating between the 3D points. The reason why it's called like a linear interpolation, let me just make this stuff. Just make a couple copies of this. So I'm going to set one output position to the box and one output position to the sphere. And if we merge these with Houdini, you do an add polygons by group. Let me just maybe do less points for now. So I think I've also messed this up. All right. So I just need to keep track of the point number. And then I only want to connect the matching points. Thank you for the Twitch Prime from Vienna, late night Vienna. So this is what I was trying to do. Basically just draw this is the interpolation path. So it's the linear path that these are traveling as you interpolate between the shapes. So if I show this and kind of template this, all of these points will travel linearly or along a line to blend between the 2 point positions. So visually, if you're ever thinking about this lerp function and what it's doing, this is the transition, or this is the path that it's drawing. If I use a channel float right here, we could do this and just set it to blend. And then as I move this from 0 and 1, let me just maybe make the wires a little bit thinner. Maybe the points a little bit bigger. So you can see. So this is the linear interpolation with the paths. So I'm going to get rid of this stuff for now. And the issue I was talking about earlier was that this box is being drawn kind of offset or not centered at the origin. Like it's all between 0, 0, 0 and 1, 1, 1. But the sphere is perfectly centered or lined up in -1, 1, -1 and 1. So when we interpolate between the two of them, it looks a little bit funky. So if we want to fix that, what we can do is just move our blend over to purely looking at the box, and we could just take our box position, and if you do minus equals 0.5, then that just shifts all of the components of the vector, x, y, and z. They're all being shifted over by 0.5. So the shifting them all is like a diagonal offset. So from this direction to that direction, like negative 0.85. So we just want to do 0.5 to go from 1, 1, 1 to 0.5, 0.5, 0.5, and negative 0.5, 0.5, 0.5. And then if you want, lastly, to get bigger, to like more closely match the outside of that circle, you might just want to do like a uniform scale. So we just do that with multiplication. Maybe 1.5. So that's just getting you more approximately to like the radius or the same like I guess perimeter of the sphere. So it's pretty simple linear interpolation, lerp, between the shapes. You kind of get the idea between everything so far? And then lastly, we just have the kind of fun jiggle spring effect. So for that, we could do one more scene distribution. Let me just stay organized a little bit. And I'm going to start with a line, go back to our kind of graphing calculator mode that we've done before. Just increase the points. So instead of the default just end points, we want some actual midpoints so we can like distort or deform the line. And we just work with a wrangle. So anytime I'm looking, kind of visualizing like an animation curve or any, this is just visualizing one-dimensional value over time. So like a float value or a slider. We were doing it for the first week with the bouncing balls and this sine wave over time. What I just do is make a u attribute, or I'm sorry, a u variable, and store the height. And then if we set the x, this is kind of our time, to u. Looks like I was looking at this on the wrong axis. So we're just stretching the height out over time. If we look at just update the y, we could do like the sine function. And again, incoming height is between 0 and 1. So if we want the full rotation or the full revolution of the sine function, we just want to scale it to 2 pi. So either order, it doesn't matter. You do 2 times pi or pi times 2, and you have the full sine wave. So there's a special kind of spring function you can use for harmonic motion, and then it kind of uses its own internal parameters, and you use different numbers or whatever for them. I'm going to use a, and you'd set that, start it at 0.15, and this, you can kind of use it to control like the dampening of the spring, like how quickly it stops oscillating back and forth. And the next one, I'm just going to call this, I usually call it W, and you'd set it to 20. And then this one will control the frequency of the spring, like the bounciness of it. Sometimes people call it mass or other things like that, but I usually just think of it as the frequency. And then for the sine wave function, it starts negative. It's kind of like a trick. Just flip it around like that, and we'll do the power. We'll set that to power of 2.7 and raise it to negative u divided by a. So u is our height, or the incoming like position along the line, divided by a. This is like a weird, funky function or whatever that you don't really need to have it like make sense in your mind. But just remembering it or writing it down or keeping it in your library of functions. So this is the spring decay function. And then the last thing you probably just want to do is add 1 to it to offset it. So what I can do over here is this one, I'm just going to go back to before we did that stuff. This will just be like y equals x. The height equals the time. There's a linear relationship between the two of them. As the time increases, the height increases linearly or in a straight line. And then this one will be spring decay. So if I template this and display this, then you can see a little bit easier what's going on is that they're both getting to the final destination or the final result, but it's just the kind of timing or the behavior in between everything. So over time this overshoots and then it recoils and then it oscillates or whatever, but becomes dampened over time. So if we play around with this, the closer you get to 0 with this, the more quickly things will become dampened. The bigger numbers you go, the longer the spring can kind of go like back and forth. And then frequency, higher numbers, the spring will kind of oscillate between the two numbers more or less quickly. So you play around with those. You could even add like parameters or stuff like that to them as well. Like channel, CHF for channel floats. Maybe I'll just go ahead and do that right now. You could just look at them like interactively. So this will be channel float dampening, and we'll just do one here. I don't know what happened. It got real dark. Turn on. Try to get a light. All right. Maybe it's gonna rain. It's gonna rain here pretty soon. So this one was our this one was our frequency, and just generate the parameters, and then you can see with them. You can get our funny spring function. It's pretty controllable. Even if the math is over my head. Yeah, it's over my head as well. It's not, I didn't sit down and draw this out with like a compass or protractor or something like that. This is something that gets shared. I think it's pretty commonly used everywhere. I'm not sure if it's a natural log. It gets used for a lot of internet programming or even like user interface design. And yeah. So this one, if you want to be cleaner about it, you could replace it with the Euler's number or E. That's what I was doing with 2.7, was approximating E with it. So if we go to edit aliases and variables, they have it. The natural log here is EA Sports. So this is a shortcut for it if you want to use it. You would put in your own numbers as well, too. But yeah, so this is actually like if you've used different... and
speaking of sound, music, and other...
Sorry about that. So if you used other interfaces and stuff, like if you look at the way that certain stuff like jiggles, like that, they use this kind of sine function for it as well. The spring, like user interface sliders and stuff, will have that kind of decay built into it. Does that? Hopefully that's a good reminder. It's more mobile and no, that was like a podcast or something that automatically started playing. It was a clip when he was introducing Little Pump for his campaign in Michigan, and he was saying, you guys come out here and see Lil Pimp. He didn't even take the time to learn his name. So we'll move the dampening back down a little bit, and could play around with the frequency. I'll usually just leave it at 20 or something like that. You could find maybe like some CSS or web programming codes, like React Spring, I think. Some of the UI stuff you'll see will get used, they'll get set to this this kind of behavior, I think. I don't know if this is the best example, but I don't know. It's a little too complex. But certain UI elements you'll see, they'll have this like oscillation, kind of natural oscillation or whatever. So yeah, this is basically, it took a long time for me to get here, but this is how I'm getting this jiggling or like overshooting and oscillation or whatever. So you can see instead of our linear blending between 0 and 1, we're getting this more like overshoot and recoil and stuff like that. So this is just user parameters. And let's make a copy of our morph. We'll just say jiggle. And this is a blend that we were doing with the float. If you want to change the range of these functions, or if you want to get rid of them, you can just click on the gear and do edit parameter interface. So for example, this frequency, I'll usually set it like up to 50. So then I can go even higher or lower with just the range of the slider. And then over here, the reason I was showing you the gear, we can use it here if I go to edit parameter interface and then just press the delete key to eliminate it. So for this situation, I'm going to have it driven with the spring function. So here I can make a variable that's just called blend and set it here. And then instead of u here, we're probably just going to want to use time, or sometimes I'll just make another variable. Could call it t and set it to time. So this way, if you want to distort time or speed it up or slow it down, it's easier. You just have one number, one variable that you need to multiply. So if I just go ahead and play this, then we get the spring. So we could change our frequency, change the dampening. Some of it's a little too wonky or too wacky. If you have like a really low mass or something like that, and a high frequency is like it will just oscillate around forever. Depending on the type of reaction or the type of delay, I don't know, just the type of the type of boing, the type of bounciness you want, you can play with these two numbers. And if you want to keep track of things, you could replace that with the $e for the natural logarithmic. So some of these, like the frequency is too high, it's almost like too quick for your, it's like too many frames per second, basically. The frequency is higher than your frames per second. So you have to be maybe a little bit careful in some situations. Natural algorithm. It's the natural logarithm. It's like this kind of, I don't know what you would call it. It's just referring to this. It's a number that is equal to itself in exponents. Yeah, I'm not exactly sure in terms of like, maybe RH2 is the better one to ask here. But you can use it like that. I think also like the Archimedes spiral, maybe we'll use it. But it's I'm not 100% sure. I just know to use it basically whenever you're generating like a logarithmic function. You're going to want to use that E number the $E, or you could approximate it as like 2.7. It's kind of similar to pi in that regards. Is like it's just a number that people will plug in as it gets used, structured kind of like that. Yeah, it's not a Houdini internal thing. It's like just more of a underlying mathematical, like pi or sine or cosine, tangents, all that business. It's just a global, universal mathematical thing. So in Houdini, they provide $E as a shortcut. So this aliases and variables, you can see E is supplied and pi is supplied, just because they're commonly used to generate these mathematical functions. So you could play around with this. Maybe we want it to last longer. And I don't know about that. Maybe 15. You get something that just looks a little bit more natural. If we did the linear, like I still have it templated here. This tends to look really robotic. There are things you can do, like sometimes for animation purposes or shading or stuff like that. You can use this smooth function. And then this will kind of do like an ease in and an ease out. So there's different, I think usually people actually smooth, makes more sense if I smooth the Y. And then the X I still want set to U. So this is like your ease in, your ease out, essentially. So for something that doesn't abruptly come to a stop, sometimes people use this smooth function. Linear is just obvious, like one-to-one. And then the spring. So it's just different types of like animation interpolation. Let's say ease in, ease out. So if you want to try out some of these other ones, this is just, we'll just keep this as lerp. Could leave t as time. Just gonna get rid of the other stuff. And we'll just say that the blend equals t. Just need to make sure that I've declared that variable. Function of x equals e to the x. It's a unique function, which is equal to its own derivative. Yeah, I'm not the best at explaining those. I've never been the greatest with these. I don't know. I just don't have as strong of a mathematical background. So the derivative is the rate of change, right? With a circle, it's like the tangent is the derivative. 1 is the only number where the exponent is the same. So with this morph, set the blend to t. One thing you'll see is that you can exceed the lerp. Like if you give it a number bigger than 1, it will just keep extrapolating that line out longer. And that's kind of what the spring, the jiggle, is hacking or making use of. So when the spring right here is going above 1, it's overshooting its final position and then recoiling and stuff like that. So that's a handy thing with the lerp or with the mix in GLSL. It works the same way. You can kind of like overdrive it or overpower it to extrapolate beyond its original position. And then if you don't want that to happen, you can just use like a clamp. This is similar to the fit function I was doing earlier, but you're basically just clamping the output range. So if I do that, you can kind of see the abrupt starting and stopping. It just doesn't look as natural. It's like more robotic of an operation. We could do, instead of the clamp, you can do a smooth. This one's always a little bit of a gotcha because the min and max comes first and then the value you want to smooth comes last. But now you can see here that the ease in, ease out is applied to the starting and ending positions of things. So then just getting a little bit fancier with it, just doing the jiggle to get a little bit funnier of a interpolation or whatever. So it's pretty cool. I'll do one more scene distribution, one more update, and then we'll just start putting some of this stuff together. So keeping this stuff kind of cleanly labeled or cleanly going, is cleanly described is a good way to go. I'm just going to keep building on that. So we'll set up, we're going to want a box. We have that. We have this sphere. We're just going to keep following the original example here. We have a cone, and then we had the human head. So let's go to our working file. Let's find the cone. Here it is. And can take this, just copy it. We have our box. We have the sphere. We'll make our cone position. We just want to set this a little bit of, just did Control X and Control V to cut and paste. Let's just do a little bit of manual stuff to rearrange this. Whoops. All right. And then if you just want to double check at the end, you can set this to the cone position. We got it. One thing I think we're going to want to do with this cone is scale the Y or the height to be a little bit higher. This just looks a little bit better. And then maybe shift it down. So this should line up a little bit better with the other shapes. I might need to shift it down a little bit more. You can always tweak it at the end if we want even more. All right, and then if you really want to be clean, you can do stuff like this: is box, sphere, cone. Then we're going to want the face or the head, And to do that, we're going to need to sample or plug in the input. I'm just going to do it before I was rotating. And this one is another pretty simple function, just a single line. And just want this to be a vector. Head position, set it equal. Can go down to the bottom and visualize it, double check. And again, this is something we're going to want to probably modify a little bit. Just take a look here. Looks like we need to scale it up. Can just multiply this by, I don't know, maybe like 3.5. If you want to do the offset, you can be a little bit fancy and do it at the end here and use the set function. And then just do like 0, 1, 0. So this will just move it down 1 unit in Y. Maybe just 0.5. Let's take a look there. So this is the same idea as doing these two operations, but just in one line of code. So it just depends, whichever, certain situations one might make more sense than the others. Whether you want to do it in one line of code or split it out into other lines of code. I just don't need to do it 2 times. All right. So we have our 3 different vectors, or the 3 lowbrow, highbrow. Yeah, I don't like to use the Egyptian brackets as much. I don't see too much of a reason behind them. Like, in my mind, they only limit your capabilities. Yeah, like, I've used them before. I think I've talked about this before, but if you use the curly brackets or the Egyptian brackets, you can use it to make to define like a 3D position or a vector, but you lose the capability of using functions, or like, I think what's called like veridic inputs, or inputs that vary per element. Like, you can only kind of define a constant location. So if I try to set a random position, this saying it can't compile it. It doesn't expect you to run functions or call functions inside of the Egyptian brackets or the curly brackets. But if we go just to set and use the rounded traditional, then you can use a function. So just by default, I'll always use set. So I have the capability to, because generally when I'm programming, I'll at the end go back and like add some randomness to things to make it look more interesting or natural. So just to always have that capability, I'll always use set instead of the curly brackets. Houdini should implicitly interpret squiggle. It might break something, or it might, I think there's certain situations, like if you're using like millions of points and you want to use the curly brackets to make like a constant, like you're going to refer to a vector a bunch of times in your code. It might be slightly more optimized, but I've never done, my programs are never run like for internal tools or things like that are used a ton of times. So I'm generally like optimizations that are just going to save you like a millisecond. I'm not too concerned with that. All right. So we have our spring. We have our 3 different variables. And now we just want to lend or cycle between them. So what let me think of the steps we want to do here. So let's just ooh, yeah, man. You have some ads to peddle here. All right, taking out the trash. So yeah, let's set up a blend, or let's make a quick cycle of things. So here we're just blending between the box and the sphere over time. One thing you can do, if I just want to do some less typing or stuff like that, I'm just going to get rid of that comment. And then I'm just going to get rid of this and just cut it, delete that, and put it in here. So we're still doing the same thing, but it's just a little bit less lines of code. So this is our first interpolation going between the box and the sphere. If I take our time, or the t variable, and offset it using the y position, or the height. I might have... Oh, okay. So the reason nothing changed is because I haven't moved the position at all, and all of my points are still at the offset time by pt num. So I'm looking to do it using the y position, but I think I want to use the y of the actual box, like that. And then right now I'm in a little bit of a weird area. So I think you want to do minus equals. There's one issue, is that with this spring function, if you have some negative numbers, so like if I do u minus equals 0.25, before your time starts, the spring just keeps getting like more and more chaotic, or extrapolates out the bounciness of it. So one way you can fix that or get rid of it is if you do or whatever your interpolation, whatever your like driver is. If you do maximum function like that, this will basically take any numbers below 0 and set them to 0. So maximum will just return the highest or the higher value between these two inputs, or these two arguments. So any any numbers below 0 just become 0 when you use it this way. So basically, we weren't seeing that issue earlier, but if you start to slide stuff forward, you just want to clamp it or cap it off like that. We could do the same thing over here, I think. You could keep doing it in one line of code. And we'll just do t equals the maximum of 0 and t minus the position y. So the reason I was setting it up like this, I think it's still a little bit glitched out. To just divide this by 10, and I don't know, I might want to offset it by 1 or something like that. Okay, subtract 1. So the reason I'm using y instead of random or ptnum, because I'm trying to get this linear like transition or like a height transition. So could maybe divide this by a smaller number. And basically over time, based off of the height of the box, your transition or your morphing is just getting like slightly offset. And you go the other way, I think, if you do t plus, then you're going like from the top to the bottom of stuff. I've kind of like scaled down that transition that it's happening really quickly, but kind of see it in this situation. Yeah, if you want to add a random number, you could break up the line. Like if it, let me just cycle some of this stuff. We'll just make a lot more points to thicken this stuff up. So yeah, if you want to add a random number, then you can break up, like if you're starting to see this line that's transitioning stuff. The reason I'm shrinking it down so much is like, this is how much you're going to offset things. So when you offset or you change the duration of things by like height is playing too much of a factor into your offset, then it kind of like hides what's happening, because everything's like overlapping too much, if that makes sense. So 14 looks a little bit better, but like when this stuff is too slow, this is like things are overlapping too much. If you do this, I don't know, I was finding some success when it's like a little noticeable. Yeah, and then if you want to add, so I just did -1 here. That's delaying this to 1 second or 24 frames into your animation. If you do an additional like minus random at ptnum, maybe just offset it by a random number, then you can see that's purely, each point is like individually getting randomly offset between 24 and 48 frames. If you scale this down again by like, I don't know, divide it by 48 to make it really small, then you'll just see like a little bit of fuzziness in this transition. If I just cut that whole portion, you can see it's just breaking up things a little bit. But depending on what you're after, it might be useful to do that. So this way we're able to transition from the box to the sphere and set the P, the output position, to that number. So we keep going, and let's just keep going here with another duplication of all this stuff. This time I want to use P because we're animating it, and then we're going to start with P, and we could end with maybe the head, and then we just need to change. Right now this stuff is, I think it's, might be okay. You're probably going to want to update this offset here though, instead of using the box position, we can now go ahead and use the Y position of the height. And I don't know, you might want to keep it with the sphere. Looks like it's okay. It might just be this random number. You chopping? Yeah, I thought it was okay. I might want to refresh it kind of. So instead of t right here, we could use time and then manually offset it to 2 seconds here. I don't know if this random. Maybe I'm just offsetting things in the wrong direction. Yeah, I don't know if it might just be like my, my numbers there were getting a little bit too, my springiness was getting a little bit too long. It could also be some artifacts because I'm kind of reusing this like PT num too many times without reseeding it. Like these numbers here are the same numbers and stuff like that. You can get some cool way of doing it without a solver. Yeah, it's cool. It's a useful implementation when you don't have as much like overhead, or you could even do this effect in a shader if you can program a lot of stuff. Yeah, I think it was just that my seeds were overlapping, like they were the same random number, which causes issues. Like it just visually can cause those like overlaps or artifacts or whatever. But yeah, it's less overhead to do things this way. With the solver, you have to like cache each step. So this way you can do little kind of like stuff that still looks natural, but it doesn't require the entire like geometry to be cached to RAM each frame. All right. So then I think I can go back in here and just use the @p.y. If I wanted to, you add the random number if you want to, or other stuff like that. All right, so we'll just keep moving. And this is going to be offset. We'll just keep going from 1 second offset, 2 seconds offset, 3 seconds offset. And we're going to go to the cone. Let's see if it works. I think it's working. And if you just want to switch from your transition here from going from top to bottom or bottom to top, that just depends whether you're adding or subtracting the Y position. So if I subtract it instead of add it, then you can flip that morph direction around. With the face going into the pyramid or the cone, I think it looks a little bit more natural going this way. because it's like the base of the cone is wider than the tip. But again, if you want to try it out the other way, you can just add the number. Yeah, I think maybe the other direction looks cool. And any of these, if you want them like spread out more, you could just divide it by a lower number. And maybe just tweak the damping a little bit. And then we're just going to want to go back to the end up back with the box, I believe. So keep going from our current point position, but we're just going to want to end up back with the box, and then we're going to want to offset or do that 1 second later. Maybe this one. Maybe this, I want to go the other direction. So yeah, we're getting pretty close to where this is. Offset by PT num. Yeah, we can add that back in. We'll just keep. And then yeah, just always. This is generally why you see people typing in random numbers. Even if they might not need it, it will kind of keep you from getting artifacts later on. And with no randomization, this is going to get pretty wild. My random is doing a couple of things for me because it's normalizing the PT num, so it's giving me a result between 0 and 1, but without it, it's going to take a long time to cycle, because basically now it will go up to like, I mean, you can, I guess, normalize it again if you divide it by num PT. I don't know how much of a difference it will make then, because the numbers are kind of generated like randomly. Like there's no specific order in the way that they're generated, I guess. But yeah, if you want to, you could keep doing it this way. You might see some artifacts after a while. Yeah, if they were sorted by X or Y, they're never. The reason I'm doing this p.y is that's my closest approximation to kind of sorting. But yeah, so this you're just offsetting or adding like a bigger variation between the transition. So like here, when we're going from the cone to the box, if I multiply this just by 0 to hide it, then we should have like a perfectly straight line. If I multiply this by 1, well, maybe I'm on the wrong. Is this the wrong one? Multiply this by 0. I think I might be doing something wrong here. So usually people will do this. This, you convert it to a float, and numpt minus 1. So then this will give you like a purely random over a second. If you wanted to do it over 1/10 of a second, you're just breaking up the transition of the height by a little bit. So all these are kind of doing similar things, but yeah, it just depends on whichever way whichever data you have to work with, and then whichever way you prefer. All right. So we're starting with the box and ending with the box. And then lastly, we'll just add in the shimmer function. So I can just copy this here. I'm just going to get rid of the spare parameter. If you also have these, I just noticed here I have an extrusion that was used from an earlier thing. I think, okay, this one it's still being used. If you ever find you have extra of these laying around, you can always just do delete all spare parameters, and that will clean them all up. But in this case, I just forgot that it was there. So let's put the shimmer in. I think we're pretty much good to go. I can use the D key and go back to disks, and then we're visualizing. So in this case, I might want the final shimmer here to be a little bit smaller. It looks like that face is a little bit smaller compared to everything. So again, I can just go in here and modify that. Maybe it's drop it down a little bit more. Might be like 5. That's looking a little bit better. So yeah, that's pretty much all there is to it. If you want to keep kind of noting your code or whatever, these are our different kind of sections here. So we're first making the different 3D shapes, or the different, defining like the point positions. And then we're doing the morphs, just the lerps or the blends, and then finally some like post effects or post process to glisten or oscillate the scale of the points with the shimmer. If you want to, you can break this up into other functions. Like sometimes I'll work that way. If you want to do a wrangle this way at the end and just do the shimmer like this. And you could, I guess, just comment this code or delete it completely. For these weekly demos, I've been keeping everything in one wrangle, which was like a little bit more, these are more about the coding process and structuring code and stuff like that. In general, with Houdini and working, I'll usually separate these out into different blocks. Just so if you want to like bypass stuff, it's easier to turn it on and off and visualize which blocks or which like chunks of code are being applied or executed. But for these demos, just because it's more about like how you're structuring your code and it's more about the process. I've been trying to keep stuff in one block of code. Also with streaming and stuff, I think it's a little bit easier if there's just one like code window or one box of code that people have their eyes on, instead of like jumping up and down the node tree or whatever. But I just wanted to point that out because some people will get is the same result, but there's just different ways of organizing your scene and stuff like that. So yeah.